Okay, in this video we are going to look at DC sweep simulation. So in the last video we discussed bias point simulation, how you can simulate a circuit to check out what are the DC voltages, DC current and DC power in different components. Now the next simulation in this video we are going to discuss DC sweep, and as I explained in the last video what is DC sweep simulation. Basically DC sweep simulation is if you are changing the value of a source from a starting value to the end value, or you can just choose any values. I mean they don't have to be in order, so you can have either values in a sequence or an order. So if you in a lab basically you are changing the power supply value from 1 volt to 2 volt to 3 volt and you're observing some voltage or current, that's in an order. But you can also change the power supply as 1 volt, 1.5 volt, 2.2 volt, 3.7 volt, so without any order. You can do both types of you can set the value of voltage source in both ways. Either it can be in an order, which is easier to do actually, or it can be discrete values that you are changing the power supply through, and that can be that can also be given as a list, as I will explain you shortly. So once you change the values of a voltage source, different values, then how different voltages and currents and power values are changing throughout the circuit. A graph of those values versus the input is called DC sweep simulation. So what I'm going to do right now, I'm going to save this. This is the last circuit that we put together. I'm going to go ahead and create one more circuit. So remember in the introductory video of PSpice, I showed you how you can create different schematic in the same project. So if you're doing different problems in a homework, you can create different schematic, and each schematic can have one page, and then you can create circuits in different schematic, and whichever simulation you want to run, that schematic has to be in top of the list under the project. So let's go ahead and create another circuit. So I'm going to put schematic 2 in the top, so I'm going to make it root, so make root, and I'm going to open this page, and I'm going to go ahead and create another circuit. I'm going to grab another source, DC source again. Let's see, DC, and I'm going to zoom in a little bit, it's easier to see. Zoom in, I'm going to move it here, and then I'm going to go ahead and change and get let's say I'll get a capacitor this time. Get a capacitor, and I'm going to get a few resistors. Let's get an inductor as well. Get an inductor, and I'm going to go ahead and get where's my resistor R. I'm going to get a resistor here, resistor here, resistor here, resistor here. So I got a bunch of resistors, and those are enough. Okay, so what I'm going to do, I'm going to rotate this inductor. Right click, rotate. I'm going to mirror it vertically so that my dot goes up, although it's not necessary here. Dot just represent in transformer which sides are in phase. R2 I'm going to keep it here. R3 I'm going to rotate again. Capacitor I'm going to rotate as well, and this resistor 4 I'm just going to leave it like this. So I'm going to keep my component in this orientation. I'm going to go ahead and connect them. I'm going to change the values later. You know what, I need to put some sort of resistor over here because the inductor is going to become short after it is fully charged, and all the current will just start going through inductor, and rest of the circuit is going to cut out of the circuit. So what I'm going to do, let's see what I should do. Perhaps I should put a resistor over here as well. Let me delete this thing. I'm going to grab another resistor, and I'm gonna create, rotate it, and align this, go ahead and connect this. So now even when the inductor is short circuit, the resistor is still there, so it will offer resistance in the path of the flow of current, and not all the current is going to flow through that branch. Okay, so let's say this is my new circuit. Okay, um, let me go ahead and change, let me call this Vs, my source voltage. Let me call this, since we are doing DC sweep, the value of this is, it does not matter because we're going to be changing the value through the simulation. Leave it at 1 kilo ohm, leave it at 10 microhenry. Let's put it at 500 ohms. Let's do this as 100 ohms. Let's put this as 2 kilo ohm, and we can change the capacitor value to 1 microfarad, and then resistance value to I don't know, 500 ohm again. Okay, let me also go ahead and open the tutorial so that we can see there are some important things that I wanted to discuss. So let me go ahead and open that as well. Let me go, where's my books, PSpice, and this is the last version. Okay, so I'm gonna go up all the way up first. Alright, so I already discussed this. Startup, we already discussed that, and this was the previous, when I wrote the tutorial. Of course, I think it was like 16, version 16 or something. So although some of the graphics will be different, but the basic functionality and the screenshots and stuff, they're pretty much the same. I mean, you went through all these. Let's go ahead and see what I want to discuss with you. I want to discuss specifically prefixes. Actually, we already discussed this, all this. Alright, this is what I want to discuss with you. So in PSpice, as you saw, K, we've been using K for kilo. Now there are other prefixes that you can use. You can use uppercase or lowercase t. So either you use uppercase or lowercase, it is the same in PSpice. In engineering, it's different. Like, and for uppercase M stands for mega in engineering, lowercase m stands for milli. But in PSpice, irrespective of it is uppercase or lowercase, it is the same prefix. So T stands for tera, which is of course multiplying factor 10 to the power 12. G, giga. Now if you have to write mega, you cannot write uppercase m because that is for milli, either lowercase or uppercase. Both stands for milli, which is 10 to the power negative 3 multiple. So for mega, you have to use one of these, MEG, MEGA, lowercase MEG, MEGA, whatever, right? That's 10 to the power 6, 1 million. K is for kilo, M is for mega, U is for micro, N is for nano, P is for pico, and F is for femto. And there is a note over here as well, because many students make this mistake. Sometimes even I make this mistake, that I am not very careful between mega and milli. So I use uppercase M for mega and lowercase m for milli. But remember, in PSpice, mega is this, and milli, uppercase m or lowercase m, whichever you want to use, that will be for milli. Okay. Alright, so we already discussed this in the last simulation, DC bias point simulation. I showed you that. I believe this is one of the exercises that you have to do. So you have to create the circuit and you have to carry out DC bias point simulation. You don't have to discuss different voltages, current, and power dissipation. You don't have to. How the circuit is going to be analyzed, we are not discussing that in this course. Of course, when you finish your circuit analysis courses, then you will know how the inductor is going to behave, how the capacitor is going to behave. So my idea was that if you have the knowledge, you can discuss the capacitor is going to become open circuit eventually, and inductor is going to become short circuit and stuff. But at this time, I really don't care. All I want you to do is to understand how to do simulations. So just carry out the bias point simulation on this circuit. As I showed you, copy the circuit, paste the circuit, and then copy the simulation and paste the simulation. Now we are doing DC sweep analysis. So I'm going to go back to our circuit. Alright, so this is our new circuit. for which I'm going to perform DC sweep analysis. Oh, we're missing one thing. We're missing the ground. So let's go ahead and grab the ground right here. Campson. Go ahead and put the ground over here, the negative side of the source, which has all of this wire. These nodes are grounded right up to this point. This is grounded as well. All right. So I'm going to go ahead and save it. Control S. It's a good idea to keep saving it in case something happens, so you don't lose your work. Let's go ahead and create a simulation profile. I'm going to call it sim2. Create. And this time we are going to run DC sweep analysis. So I'm going to go ahead and choose DC sweep. Now observe in DC sweep, it asks you what is the name of first of all, you are doing only one sweep source. Sometimes in the circuit you have two sources and you can do sweep for both sources. But we are doing only one sweep, one source, and we are sweeping that source. So primary sweep only. Okay. What is the name of your voltage source? This is the name right here, VS. So put that name over here, VS. Okay, this is a voltage source, not a current source. That's why I chose voltage source. All right, next sweep type. You can do either linear sweep or you can do logarithmic sweep. So logarithmic sweep is going to keep x-axis. Each tenfold of the frequency is going to have the same scale. Let's do the linear sweep right now. Let's say I want to do in an order. So I start with 0 volt. I increase my value with 0.1 volt, and you don't have to put V if you don't want to, and then I want to go all the way up to 10 volt. Now remember, anytime you are putting a value, make sure you do not have any space between the prefix or the unit and the value, otherwise you will get an error. So if you're putting 10 volt, there should not be a space between 10 and volt, right? Likewise, if you're doing 10 millivolt, there should not be a space between 10 and milli, okay? And likewise milli and volt. So these are the parameters that you have to set. Now if you wanna, instead of having a start value, end value, increment, if it is random values that you're changing, then you can just create a list over here, and a list has to be separated by commas. So you can go 1, 2.2, 4.5, and those values will be adapted by the source. I'm just doing right now, linear with specific values. So go ahead and apply, press OK, and go ahead and simulate it. Alright, observe, it's no longer gray, right? It's no longer gray. Wait a minute, what happened? -1, 0, 1, why it is going? I'm going to go back and check real quick. Actually I don't have to go back. Let me open the simulation editor from here. What did I do? 0 and value 0.1 and 10. So why it is doing -1, 0 and 1? This is strange. Let me see. Okay, 0 volt. Oh, end value, my bad. I thought it's increment as 10 volt. Last value and increment is 0.1 volt. Oops. Okay, my bad. Apply, okay, and then go ahead and run it again. You can run it either from here or the other window. Alright, here you go. So from 0 to 10 volt, right? And right now it's black. You can change the screen color, the background color of the simulation, going into tools and options. So here you can under color setting, you can choose the foreground color, background color, and all those things. So they are discussed in the tutorial as well. Anyways, so here is status. Everything worked out. There is no error. And this is the cursor window. We're gonna discuss that. So right now there is nothing here, right? How are you gonna plot the voltage, current, power, stuff like that? You have to go back to your circuit. Now you are going to use different types of probes. You have 4 probes over here. Voltage marker, level marker. Now the first one, voltage level marker, will measure the voltage of any node, any point with respect to ground. So anywhere you put this, it's going to be measurement of voltage at that point with respect to ground. Now if you have a component connected between that point and ground, then basically it's going to be measuring the voltage across that component. But if your component, for example, R4, R4 is connected between this node right here and ground. This point is ground. So if I want to see how the voltage is changing through R4, across R4, I'm just going to grab the voltage marker. I'm going to put it here, wherever you want to put. It's the same one, right? I'm going to put it here. And then when I go back, this is how the voltage across R4 is changing. As the source voltage is changing, this is source voltage. So voltage V, Vs. Vs is our source. So V is the voltage. So voltage across Vs. As the voltage across the source voltage is changing from 0 to 10 volt with an increment of 0.1 volt, the voltage across R4 at node 1. So where I put the marker, this node is node 1 and this node is node 2. And you can see that R4 2, right? So your marker is placed at R4 node 1 and R4 node 2 is grounded. That means your marker is basically measuring the voltage with respect to ground. In other words, it is measuring voltage across R4. So you use a single-ended probe, voltage probe, only if you are measuring voltage across a component for which one of the end is grounded, because the single-ended probe always measures the voltage with respect to ground. So wherever you're going to put this, it's going to measure the voltage at that point with respect to ground. So observe, this is how the voltage across R4 is changing. Right? It's going from 0 volt all the way up to 1.6 volt. Okay. Now you can also change the width of this line. You can change color of this line. If you do right click, if you go to trace property, then you can change color of this, whichever color you want, let's say pink, and you can change width of that. Sometimes it's good to change width of that so you can see it easily. You can change the pattern if you want. I don't want to change the pattern. Okay, so it became thicker. Sometimes it's easier to see if the line is thick. And the same color is going to be the legend to show you that what voltage you are plotting, because you can plot multiple voltages on the same window, right? Okay, let's do that then. Let's go back, and let's say you also want to measure the voltage across R2. Now can I use this same probe and put it here, and should I claim that the green voltage, let me go ahead and make it thicker again, just actually let me leave it right now. Can I claim that this voltage is the voltage across R2? No, I cannot, because remember, the single-ended probe is going to measure the voltage from this point, which is node number 1 of R2, with respect to ground. Now, is R2 connected between this point and ground? No, it is not. It is connected between this node and this node, which is basically, not connected to ground. This node is not connected to ground. It's connected to R3, C1, R4, but not connected to ground. That means this probe I cannot use to measure voltage across R2, across R2. I cannot use the single-ended voltage probe. So I'm gonna highlight it and hit delete. I'm gonna delete it. So which probe can I use to measure the voltage across a component? Double-ended probe, the second one, voltage differential marker. So when you grab this, you're gonna click once, it's gonna put the positive side of the marker. Click on the other side, it's going to put the negative side of the marker. So this is the differential probe, voltage differential, and this is specifically used to measure voltage across a component. And in general, you use this probe if one end of the component is not grounded, so single-ended probe is not going to measure the voltage across that component. So you have to use the double-ended probe. Now you can use it for any component, because it's basically measuring the voltage across that component irrespective if the other end is grounded or not. But it is just redundant to use this if the other end is grounded. It's better to use a single-ended probe if the other end of the component is grounded and you're trying to measure the voltage across that component. But again, if the other end is not grounded, you must use potential difference probe to measure the voltage across that component. And if the other end is grounded, if you use potential differential probe, then there is no harm done. It will still measure the correct voltage. So now you can measure the correct voltage drop across R2, which is this. So as the input voltage is changing, voltage across R2 is dropping like this. Again, I'm going to go ahead and I'm going to change the width. I'm going to leave the color but change the width so that I have same width for both lines. Here you go. Good. Alright, let me show you one more thing. Now let's say you want to measure the current that is changing through a component. So I'm going to go ahead and take the third probe, which is the current marker. And current marker you cannot put on anywhere except at the edge of the component, at the node of the component. So let's say I want to measure the current passing through R3 here. So I cannot put it here. It's going to give me an error. Current marker will be ignored unless connected to a pin. So you have to use it at a pin right here, where the wire and the component is connected. That's a pin. Okay. Alright, let me go back. What do you see? You see that the red one, which is down here, is almost zero. What does that mean? The current is zero? Actually no, the current is not zero, but the scale of the current is in milliampere. So that scale, if you compare with the scale of these voltages, is extremely small. Hence the current is basically pushed down to the x-axis to the zero value. So if you are plotting different quantities on the same plot which have significantly different scales, then do not plot that on the same plot. So I cannot really plot the current on this plot with my voltages because it will show you just the zero current. So what should I do? I'm going to go ahead and delete that marker. And what I'm going to do is, so I can do two things, right? If you already have captured this, then perfectly good. You can remove the markers. You can remove these markers. So, this will become, this is going to become simulation. This is going to become blank again. And then you can put current marker and then it will adjust with the scale of the current. But if you do want to keep the voltages, then what I can do, I can go to plot and I can do add plot to this window. So it's going to add another plot to this window. And then I have selected this. I can select either this. By clicking on the bottom plot, I can select on the top one. And then once it is selected, then I'm going to go back and then I'm going to take the current marker and I'm going to put over there and observe. Now you can see the current because now the scale of this plot and these plots are totally different. This is for the current, so the scale of the plot is in milliampere, as you can see, 400 milliampere, 800 milliampere, and this is volt. It's going from 0 to 2 volt basically. So this is your current right here, negative IR3. Why negative? So this is another thing in PSpice. If let's look at let me check one thing. This is R32 and this is R3. This is node number 1 and this is node number 2. In general, if the current is entering in node number 1, it shows the symbol. It shows the symbol of positive current, positive I1. And if it is entering in node number 2, it shows the symbol of negative. So that's the only thing in PSpice. Although it's the same current, right? Coming in and going out is going to be the same current. But it just shows that, oops, I put the voltage probe instead of current, and go back and delete that and put the current probe. So although it's the same current, it's of course it's a positive current going into the voltage, going into R3, but just the symbol is showing negative IR3 because you connecting the probe to the second node R2, I mean the opposite side of the resistor. So the current is increasing from 0 to whatever. Now another thing, observe, if I put this here at node number 1 of R3, Go back, observe what happened. First, observe the current. So you're connecting to the first node. The label of the current is IR3, but observe what happened. It starts showing you negative current. So that's another funny thing in PSpice. If you are measuring the current entering into a component, it will show you positive current. If you put the probe to the node where current is leaving the component, it shows you negative current. So that's another funny thing in PSpice. Although it's the same current, entering in the component is the same thing as leaving the component. So make sure if I ask you to show me the simulation for the current, make sure put your current marker where the current is entering, that is to show the positive current. So I'm going to put my marker on top, and that will be the current passing through R3. Okay. If you have to show power dissipated in a component, I'm going to add another window. So I'm going to go ahead and add another window to the plot and select this. And let's say you want to show how much power is dissipated in R5. So you're going to grab the last probe, which is the power dissipation probe. And power dissipation probe goes on top of the component, not at the pin, not anywhere else, on top of the component. So you connect it on top, and then you go and observe, and it will show you the power is dissipated in that component in this fashion when the input is changing from 0 to 10 volt. So this is your DC sweep simulation. I'm going to go ahead and let's say I change this trace information. Oops, it's just the information about the trace property. Let's say I change it with to a yellow color. I change the thickness of the line as well, and the power I go ahead and trace property, I change it to, I don't know, teal color or green color, whatever is that, light green color, lime green color, whatever you call the thickness. Okay, all right. So let's go back to our file that you have to submit, or you don't have to submit. This is just an example. Let's say if you have to submit this, it's a homework. Then let's say this is my exercise 2. So I'm gonna go ahead and I mean, if you have the pins the marker connected, perfectly fine. Keep them connected so I can see you are putting the correct markers at the correct nodes. And let's go ahead and copy this. Copy the whole thing and Control C. I'm gonna go back, save, and then I'm gonna go ahead and copy the simulation. So this is my simulation. Now there are multiple ways to copy simulation. One way is if you go to Window, it shows you and it gives you an option, copy to clipboard. You can use that option as well, and it asks you change the background from black to white. You can do okay, or you can just leave it as it is, whatever. So that's one way to copy the simulation. The other way to copy the simulation is just go to the snipping tool, screen snip, and then you can just snip this screen. And if I ask you in future, show me the cursor window and stuff, you can snip the cursor window as well. So there are multiple ways to copy this, whichever way you want to do it. The main point is to copy the simulation, go back to the Word file, Control V, save, print the simulation. And since I copied the clipboard and it gave me the option that background, do you want to change the background from black to white? And I said yes. So that's why the background is changed to white. If you just use the snipping tool or print the screen, then of course the background will still be black, which is perfectly fine. You don't have to print it. If you are printing this thing, then of course I will force you to actually keep the background white so that you don't waste printer ink. But I mean, you're just submitting it on canvas, so irrespective whatever color you're using, it's not going to, you're not printing it, so no harm done. So again, if these two problems are the problems that you have to submit, this is how you're going to submit. You're going to put the circuit, put the simulation, exercise 2, put the circuit, put the simulation. You're going to go ahead and save this file, and you're going to name the file as your first name underscore last name underscore homework 1. Let's say if it is homework 1, so HW1. And you have to save it in the PDF format. So you can keep a Word file, you save it by default as a Word file, and then make sure save as and convert it into a PDF file, because I want you to upload the PDF file on Canvas. Okay, so this is how you're going to submit your homework. If you have more problems, exercise 3, exercise 4, just in the same Word file you can keep adding the exercises, circuits, and simulation for each exercise. If I ask you any question about it, for example, some of the problems require you to measure the voltage, measure the gain of the circuit for the amplifier and stuff. So you will have to calculate, you have to observe the voltages, take the ratio between the output voltage, input voltage to calculate gain. So you're just gonna type basically that this is the gain of the circuit in Word file, and then of course you're just gonna submit that. So this is how you're going to submit your homework, and this finishes up DC sweep simulation discussion.